This will be a video for section 12.3. We're going to do the experimental probability of compound events. In the last section, we didn't do compound, we did simple. But we only had one possible outcome. So like if I reach in this container, I draw a pink. Or if I reach in this container, I draw a black. In this case, though, we're going to do a compound event where, like, what are the chances of me rolling a 5 and drawing an orange? So a compound, we're going to have more than one thing that we're recording. Here at the start, we're going to do an example of a compound probability event. So a compound event is an event that includes two or more simple events, such as flipping a coin and rolling a number cube. A compound event can include events that depend on each other or are independent. Events are independent if the occurrence of one does not affect the probability of the other event, such as flipping a coin and rolling a number cube. Those don't really affect each other. So we're gonna fill out this page. We're gonna do a little bit of a lab here. I'm gonna do it here on camera, but if you want it, you could get a number cube and a coin, and you could do your own results here. For A, what are the possible outcomes of flipping a coin one time? Well, what are the possibilities if you flip a coin? Well, you can get heads and you can get tails. So there's two possibilities. There's tails, and I colored the heads black so it's easier to see on camera. Don't worry, it's plastic. It's not even real, but it should work for this lesson. What are the possible outcomes of rolling a number cube? 1, 2, 3, 4, 5, and 6. 6 sides. We got 1, 2, 3, 4, 5, and 6. So for C, we're going to complete the list for all the possible outcomes for flipping a coin and rolling a number cube. Well, we could get heads in 1. We could get heads in 2, heads in 3, heads in 4, heads in... All right, so we could get heads 1, heads 2, heads 3, heads 4, heads 5, heads 6. And we can get 1 through 6 with tails as well. So tails 1, tails 2, tails 3, tails 4, tails 5, tails 6. H1 would mean the coin landed on heads and the number cube showed a 1. Yeah, I know. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possible outcomes for this event. So we're going to fill out this table. We're going to do this 50 times. I probably won't do 50. We'll see how long it takes. And we're going to tally the results. So let's see. I'm going to do it in this so I don't lose them. But we got 6 heads. So 6 heads. 1 tails. 4. Let's see. There's some proof. I'm just probably going to... Let me see. Should I do it like this? 4 tails. So 4 tails. 5 tails. 5 tails again. 1 heads. All right, we got 2 heads. 2 tails. I don't think we'll do 50. 4 tails. Here we go. 5 heads. 6 heads. 6 heads. 6 heads. How on earth are we getting 3 times in a row? 1 heads. 2 heads. 3 tails. 1 heads. Another 6 heads. 6 tails. 6 tails. 6 heads. 4 heads. Get it? 4 heads. 1 tails. If you want to skip ahead in this video, that'd be fine. Just up to where I draw a nice star right here. 1 tails. 2 tails. 3 heads. Another 3 heads. 5 heads. 2 tails. 6 tails. 5 heads. 2 heads. 6 tails. 1 tails. 6 heads. 5 heads. 4 tails. 2 tails. 6 heads. Let's count. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 34, 35, 36, 37, 38, 39. We got 11 left. 5 heads. 6 heads. 4 tails. 6 heads. My goodness. 6 tails. 6 heads. This is crazy. This is not random. 1 tails. 5 heads. 4 tails. 1 tails. Let's count one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 20, 25, 30, 35, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50. Got it. 50. All right, we'll draw a nice little star here. All right, we've got 50 trials here. We got a lot of 6 heads. In fact, we got a lot in a row, which tells me my experiment was probably not perfectly random, but I didn't want to keep flipping a coin. I'd probably do it a little differently if I did this lesson or I did this experiment again. Based on your data, which compound event had the greatest experimental probability and what was it? So the greatest was 6 heads, or H6. And it had, let's see, 5, 10, 11, 12 out of 50. As a percent, well, that's 12 out of 50 is the same thing as out of hundreds would be percent, would be 24%. That is incredibly unlikely that happens again. But I don't think my plastic box was perfectly random, so 24%, and as a decimal is 0.24. So we'll do that in all three. And our least was a tie between head 4 and tail 3. Those were both 1 out of 50, which is 2% or 0.02. All right. For F, did you expect to have the same probability for each possible combination of flips and rolls? Why or why not? You kind of expect to do that, but remember in the last lesson, we talked about the thing I said that's called the law of large numbers. The more and more and more you do, the more equal results we will get. However, we only did 50 trials here, so we only did 50 trials. So we would probably need to do a lot more trials before our results become pretty evenly balanced. We would need many more trials. Like we would need probably hundreds before these start to balance out, because experimental probability is random. But if we did like 10,000 of these, our percents are going to be probably pretty well even. Because the law of large numbers says the more and more and more and more and more and more you do this, the more close to your theoretical probability, where each one would be 1/12, 1 divided by 12. Each one would be about 8.3% of the time. In this case, we got some that are 2, and we got one that's 24%. If we did 10,000 trials, those would probably balance out over time. So let's go ahead to the next page. Let's see what we've got. Calculating the experimental probability of compound events. So here's what they've got. They've got the amount of green salad and a 2-piece chicken, macaroni and cheese and a 2-piece chicken, French fries and a 2-piece chicken, coleslaw and a 2-piece chicken, all those with a 3-piece chicken. These are how many people ordered these things. So this food truck, they got to make sure that they have the amount of things, the amount of supplies that they're going to need for every single day. So they check out the experimental probability and see what people order. So they have a total of 330 customers here in this. 33 plus 13 plus 22 plus 55, because 55 people got a 3-piece and a mac and cheese. So each of these needs added up to find our total. So we found the total number of trials. We add up all 8 of these numbers. That's 330. So to find out the experimental probability, someone gets a 3-piece with coleslaw. Well, 3 pieces, coleslaw. That's 55 people. So 55 out of 330 total. We can reduce this. We can divide by 5. 55 divided by 5 is 11. 330 divided by 5, I think it's 66. Let's check. 330 divided by 5 is 66. And that you can divide that one by 11. That's 1/6, which is what they got here. 1/6, or 1 divided by 6, is about 16.6 repeated percent. That's how many people got 3 pieces and coleslaw. The most common thing people got was a 3-piece and French fries. That's probably what I would get. I'd probably get a 2-piece and French fries. I don't know. I don't really like chicken anymore. Depends on what it looks like, I suppose. What would you get? I'm just kidding. All right, next question. Down here on the bottom, we've got, we're going to answer this one. We've got drink sales for the afternoon at a school carnival were recorded in the table. What is the experimental probability that the next drink is a small cocoa? So a small cocoa is right here. Well, that would be 60 out of how many? Well, we got to add up all of our possibilities, because 77 people got a small soda. So 98 people got a small water. So 77 plus 98 plus 60 plus 68 plus 45 plus 52. We got 400 people. We can reduce this. Divide by 10, 6 over 40. We can reduce again. Divide by 2, 3 out of 20, and that's actually going to be done. 3 divided by 20 is 0.15, 15%. Okay, so that is the experimental probability. The next drink is a small cocoa. Next page. We can use a simulation to make a prediction. You can use a simulation or model of an experiment to find the experimental probability of compound events. So what they're doing here is, at a street intersection, a vehicle is classified as either a car or a truck, and it can turn left, right, or go straight. So they have 50-50 chance on car or truck. So that's like flipping a coin, maybe. So they would flip this coin. Heads is a car, tails is a truck, maybe. And then they can go left, right, or straight. So what they did is they made a spinner. We had an example of a spinner like this where each one was 120 degrees, because that adds up to 360. So they're perfectly balanced, perfectly even for our spinner. And they would spin and get the probability of a car going left, right, or straight, because it's equal probability, apparently, of cars going left, right, or straight here. So we have 6 possibilities, 6 outcomes. It can be a car that goes left, a car that goes right, a car that goes straight, a truck that goes left, a truck that goes right, a truck that goes straight. And now we want to look at our results. They had 8 cars went left, 9 trucks went left. 6 cars went right, 11 trucks went right. 9 cars went straight, 7 trucks went straight. So the probability of a car that goes right, well, a car that goes right is 6 out of, when we add them all up, it's 50. 6 out of 50 is 3 out of 25 in simplest form, 0.12 and 12%. Don't worry about writing on this one. We're going to go to the next page, and we're going to answer these. We're going to finish this page, and then we'll probably almost wrap it up. I think there's a couple on the next page I'd like to talk about. A jeweler sells necklaces made in 3 sizes in 2 different metals. Use the data from a simulation to find the experimental probability that the next necklace sold is a 20-inch gold necklace. Well, let's find our 20 inches is here. Gold is here. So we have 2 out of however many. So our probability is 2 out of 12, 16, 51, 22, 8, and 2. So the total amount that we have, I got a weird number, so I want to just make sure I was right. I got 111. 12 plus 22 plus 16 plus 8 plus 51 plus 2. 111. So 2 out of 111. 111 can't be divided by 2, so that's going to be simplest form. 2 divided by 111 is 0.018. 0.018 as a percent is 1.8%. We're going to round it. We'll leave it at that. Use the data, find the probability of a 20-inch gold necklace. There we have it. Out of 111 necklaces sold, 2 of them were gold 20-inchers. So we have a 1.8% chance of that happening again. Number 1. A dentist has 400 male and female patients that range in ages from 10 to 50 years old and up, as shown in the table. So we've got a total of 400. We're not going to have to even add these. They told us already it's 400. Okay. What is the experimental probability that the next patient will be female and in the age range of 20 to 39? So we have 50 total females from 22 to 39 out of 400 people. They already told us that. We could add all these up. I mean, we get 400. So 50 out of 400, let's reduce this. Simplest form, let's get rid of the zeros. Divide by 10, divide by 10. 5 out of 40, divide by 5. 1 out of 8. 1 divided by 8 as a decimal is 0.125, and as a percent is 12.5%. And that's it. That's the answer. Probability is 50 out of 400. Simplify it. Simplest form, fraction. As a decimal, 0.125. We do 1 divided by 8 times 100 to make 12.5%. Number 2, at a car wash, customers can choose the type of wash and whether to use the interior vacuum. Customers are equally likely to choose each type of wash and whether to use the vacuum. So we have 3 types of washes: standard, deluxe, and superior. And then there's a 50% chance whether they use the vacuum or not. Use a simulation to find the experimental probability that the next customer purchases a deluxe wash and no interior vacuum. So we're going to have a table that has 3 options on the top, 2 on the bottom. So this is a yes vacuum, no vacuum, standard, deluxe, superior. Standard, deluxe, superior. So we got 6 possibilities here. What's a way we could do this? Well, we could do it with this. Heads and tails is our yes or no. So let's say heads is yes. Or no, I'm not going to say yes. We need to say heads. Let's put all these words. Heads is vacuum. Too many C's there, Mr. A. Vacuum. Tails. No vacuum. We'll say 1 to 2 on the die is standard. 3 to 4 is deluxe. And 5 to 6 is superior. So what we do, let's go like 10 times. We'll flip our coin, roll our die. We got a heads 1. So heads 1 will be standard and vacuum. Heads 2, we got a yes and a deluxe. Heads 2, oh, we got another one. Heads deluxe. Tails 3, so we got somebody who would do the superior. Heads 4. I wonder if I put that in the wrong spot just then. Heads 4, I think I did. I know, I'm looking back. I think that was supposed to be a standard because it was a 2. So I'll fix that next time I get a 1 heads. A 3 heads. Tails 2. There we go. So this is what we could do. We could decide, okay, this many people got that. This many people got that. This many people got that. This is good enough as a description. Other ways we could do it, we could do a spinner. A spinner that had, we could have 2 spinners. One of them was divided up the middle where we had vacuum and not vacuum. And we had another spinner that's broken into thirds where it's standard, deluxe, and superior. We could do marbles or color cubes, we could say, okay, well, if they get red, that's no vacuum, and blue is a vacuum. Let me move this here. So this is vacuum and no vacuum, so red and blue. And then with the other one, we got deluxe, green or black will be superior, and there's standard. So we'd randomly draw from 2 different bags. We randomly pick one of these. Oh, they got a vacuum. And randomly draw. Oh, they got the deluxe or superior, whatever numbers or things I said. We could have 2 different random bags, and we just reach in. Probably do it with decks of cards. Somehow, maybe you get rid of one of the suits, and you're doing you're doing hearts, diamonds, and spades, and you take out the clubs, and now you've got 3 different sets of suits that you pull one out, you get a heart. Oh, that's superior. You pull it out, you get a whatever. Many ways you could simulate these. How do you find the experimental probability of a compound event? Well, let's see what the book said. Let's use their words because I like their words. To find the experimental probability of a compound event, maybe they didn't give us words. Here, using recorded data. All right, they didn't give us like vocab for this, so let's go ahead and make up our own. We've got down here on the bottom, the experimental probability of a compound event. We need to find the amount of outcomes and divide by the total number of trials. That's pretty much the same answer we had for the number 3 on the last section. There are a couple on the next page I'd like to really briefly talk about. So let's see, number 4, not going to worry about number 4, but let's do number 5, 6, and 7. That's all we're going to do here. And I'll have you do 5, 6, and 7 as well. The school store sells spiral notebooks in 4 colors and 3 different sizes. The table shows the sales by color, by size and color for 400 notebooks. So we have a total of 400. All right, we don't have to add these all up. They already told us how many it would be. What is the experimental probability that a person will buy a red notebook with 150 pages? Well, red 150, that's going to be 60 out of 400. Reduce it to 6 out of 40. Reduce again, 3 out of 20. As a decimal, I think it's 0.6. Let's check. 3 divided by 20. No, I wasn't right. 0.15 and 15%. Number 6, what is the experimental probability that the next customer buys any red notebooks? Well, that's going to be all 3 of these added together. So we've got 55, 60, and 23. So that's 138 out of 400. We can divide those by 2. 200, 138 divided by 2. 69. That works with 3. That doesn't work with 3. So 69 out of 200. 0.345 equals 34.5% of the time the next person's going to buy a red. How many possible combined page count and color choices are possible? Well, 4 times 3. We've got 4 up here. We've got 3 here. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possibilities. How does this number relate to the number of page choices? Oh, okay. There's 12 choices. There are 4 colors and 3 sizes. So 4 times 3 equals 12 choices. Got it. All right. So as long as you got number 5, number 6, and number 7 done, I'll say right now you do not have to take a picture of these ones, okay? So just put them in your book. I'd like a picture of pages. This page. I want this page as a picture, and the first page. So let's do just this page where we did our experiment, and this page. So just the 2 pages. That's 384, and I think it was 381. 381 and 384. Let me know if you have any questions.